All right, good evening. My name is Hunter, and this is content review for Chemistry 222. Today we're going over thermochemistry. Um, a couple of admin things before we get started. I will be live streaming this content every Friday at 4 p.m. We've had some problems with the internet today. It came back online not too long ago, so hopefully it remains stable. But if I cut out, that is why. You'll be able to find all of the recordings for these live streams on the PSU Learning Center YouTube channel, which you should have links to. And you are more than welcome to participate live as well or drop comments on that channel. I will respond as I can. My contact information is not on here, but I'm going to add that really quick. Let me put it on the right document here. Burp. That's not the one. That's it. Okay, cool. So that's what I've got. The list up here at the top of your screen is what we'll be going over each week. You can use your OpenStax textbook to look ahead and do some of these practice problems. Some of these questions will have links to the answer key within the textbook, and some will not. I'll be going over all of them either way. Let's jump into the content. So this first set of problems is just simple calorimetry. How many milliliters of water at 23 degrees Celsius with a density of 1 gram per milliliter must be mixed with 180 milliliters, that's about 6 ounces, of coffee at 95 degrees Celsius so that the resulting combination will have a temperature of 60 degrees Celsius. Assume that coffee and water have the same density and the same specific heat. So the equation that we're working with, first we have to know what we're solving for. We're asked for milliliters of water, but the calorimetry equations that we're working with don't deal in volume. And so this added bit of information here of 1 gram per milliliter is really, really important. That allows us to kind of use grams and milliliters interchangeably in this specific case. If it didn't, we would have to do some dimensional analysis to figure out what the mass is, because the equation of interest here is this one over on the right. This is Q, which is heat, equals C m delta T. And I'm actually going to erase this and rewrite it mc delta T, because this is a little bit easier way to remember it. If you're a pre-med student, you know you'll have to take the MCAT exam at some point. So heat equals MCAT is what that looks like. So M, of course, is mass. C, lowercase, is the specific heat capacity, and delta T is the change in temperature. That's the one that we're dealing with. We also need to know that when we are dealing with calorimetry equations, we're measuring one change in temperature in we're measuring the change in temperature of the analyte by measuring the solution. So we're measuring it indirectly. And this works because of this phenomenon where we have the heat of the solution is equal to the inverse of the heat of the analyte. So we can set that up as an equation. Yeah, C1 times M1 times delta T1, we'll call that water. This is our solution in this case, equals negative C2 times M2 times delta T2, that's our coffee, right? And then we just need to plug in the values that we have. So the specific heat of water is tabulated, and I've brought the relevant chart in here. But the specific heat of water is also should be one that you commit to memory, because it's also the value of a calorie. And that is 4.184 joules over grams degrees Celsius is your unit there. But I digress. So 4.184, we've got that on both sides here of our equation. We're asked how many milliliters of water we need. We know that this is functionally interchangeable with the mass. So this is what we're solving for. Mass of water is our variable. And then delta T. Delta T is your final temperature minus your initial temperature. We know that we're trying to get to a final temperature of 60 degrees. And we're starting with 23 degrees Celsius for our water. We're given 180 milliliters or 180 grams of coffee. Remember that they have the same density as the water. And then our delta T is, we want a final of 60 degrees Celsius, and we're starting at 95 degrees Celsius. So let's run those numbers. Actually, if you're watching the recording of this, pause, run those calculations. I'm not going to whip out my calculator because I actually prepared and did this, but we can also just set this up a little bit differently so that our variable is on one side of the equation. 4.184 times 180 times 60 over, or minus 95, all over, that would be positive. The reason I've written it this way is so that we can simplify this equation a little bit further, because we have the same specific heat capacity on top bottom, we can eliminate it. This simplifies our math a little bit here too. Okay. So now we just do 180 times 60 minus 95 over the quantity 60 minus 23. And our final answer should be 170.27 grams. And again, if we had to do a dimensional analysis, we would throw in our density here, and that would give us approximately 170 milliliters. And that is your final answer. All right, next question. Still on calorimetry. Make sure you can see okay. Yes, you can. A 0.5 gram sample of potassium chloride is added to 50 grams of water in a calorimeter. And I'll zoom out a little bit so you can see this image of our coffee cup calorimeter here. If the temperature decreases by 1.05 degrees Celsius, what is the approximate amount of heat involved in the dissolution of the potassium chloride, assuming the specific heat of the resulting solution is 4.18 joules over gram Celsius? Is the reaction exothermic or endothermic? So again, we're dealing with this same equation to start, where the heat of the solution equals mass times specific heat times the change in temperature, right? That's a good starting point. We have all of the information here we need to calculate the heat of the solution, and in calorimetry, we're measuring the heat of the reaction indirectly. So let's start here. Because we're measuring not just the quantity of water, we're measuring the quantity of water plus the analyte, which is that potassium chloride. We have not 50 grams, but 50 plus 0.5 grams. We have our specific heat, it's 4.18, and we have a change in temperature decreases 1.05, so negative 1.05 equals Q solution. And if we run that, we should get negative 221.64 joules. And yeah, I'm going to go ahead and show the unit conversions here. So I'll set this up again. We have our mass times our specific heat, which is in units of joules over grams times degrees Celsius, times degrees Celsius. Degrees Celsius cancel out, grams cancel out. We're left with joules. It's just a good practice to check your units at the end to make sure that you're on the right track. But I'm going to do this in a different color. We need to be reminded that this was for the heat of the solution. They're asking for the approximate amount of heat involved in the dissolution of the potassium chloride. So they're looking for the heat of the reaction. And because Q solution equals the inverse Q, I'll just write reaction here. Our answer then is positive 220, we'll round it up and say 222 joules. And then finally, is the reaction exothermic or endothermic? If we're looking at our signs, negative would generally mean exothermic, heat is being lost from the system of interest. A positive sign means that it's pulling heat in. By definition, that is endothermic, endo into exo, out of. So endothermic. All right. Question 26. When 50 grams of 0.2 molar sodium chloride, aqueous sodium chloride, at 24.1 degrees Celsius is added to 100 grams of zero point 0.1 molar silver nitrate, aqueous, also aqueous, at 24.1 degrees Celsius in a calorimeter, the temperature increases to 25.2 degrees Celsius as sodium chloride solids form. Excuse me, as silver chloride solids form. Assuming the specific heat of the solution and of the product is 4.2 joules over grams Celsius, calculate the approximate amount of heat in joules produced. So calculate the approximate amount of heat in joules produced. Very similar setup here. So Q solution equals MCAT. We're given a mass of sodium chloride. We'll start there. Plus the mass of silver nitrate. We're given a specific heat of the solution and products. And we're given a change in temperature from, our final was going to be 25.2 minus an initial temperature of 24.1. Come on. Yeah, so far so good. So running that out, we get 150, 4.2, 1.1 multiplied equals 693 joules. So this one really was a simple plug and chug. If you know the formula, you know your variables, you can just work right through it. Let me make sure I'm not forgetting anything here. Yeah, cool. Yep. And again, just to drive home the conceptual part of this, the temperature of the solution increased, which means that the reaction lost heat into the solution. So 693 joules were released from the reaction. We don't need to put a negative sign here um, because of how the question is, where we shouldn't. We shouldn't have to. Because of how the question is phrased, we can just write it as an absolute value. All right, so getting into enthalpy. Um, Conceptually, if your pressure remains constant, then the change in enthalpy is equal to the change in heat. So they can be used kind of interchangeably. The terms can be used interchangeably. So how much heat is produced by burning 4 moles of acetylene under standard state conditions? Standard state conditions being like 1 atmosphere, 25 degrees Celsius. Yep. Yeah. Um, this is something that we would go to our tabulated values for. And here it's table 5.2. And we're looking for acetylene, which is right here. And so this reaction, they've actually just given it to us as written. I've rewritten it up here under the question. Um, and you get an enthalpy of combustion of negative 1,301.1 kilojoules per mole. So that would be per 1 mole. We're given 4 moles. So we need to do a little dimensional analysis. We're given, I'm going to zoom in here a little bit so that it's easier to see and to write. We're given 4 moles of acetylene, and per mole of acetylene, our tabulated value produces 1,301.1 kilojoules equals 5,000, negative 5,204.4 kilojoules. This negative sign is important because through combustion, energy is being released. We know that this is exothermic. The question is not asking it. I just kind of like to hit this home. Um, how much heat is produced? The answer key in the textbook gives you a positive value. And so the reason I'm going back here and kind of making note of the negative sign on here is just a reminder to be careful. The reason that the answer key gives a positive value is because of the wording of the question, how much heat is produced by burning 4 moles? So you can write it as an absolute value as written in the equation here. It's the combustion releases 5,204.4 kilojoules. That release is communicated through that negative sign. So just be careful with that. All right. Question 49. When 2.5 grams of methane burns in oxygen, 125 kilojoules of heat is produced. What is the enthalpy of combustion per mole of methane under these conditions? So here we could get away from the tabulated values. Since they're giving you the amount of energy produced, we don't really need to worry about what the conditions are. Um, but let's run the dimensional analysis. We know that this is per we're given a mass. We're trying to get to number of kilojoules per mole of substance. So first we need to figure out how many moles of methane we have. And to do that, we need to know the molar mass of methane. Methane is one carbon with four hydrogens attached to it. Molar mass of carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. The sum is 16.05 grams per mole. So back to our dimensional analysis, we're given 2.5 grams. We divide that by 16.05 grams per 1 mole of methane, gives us 0.1515 moles of methane, that's CH4. Now, they told us that 125 kilojoules of heat was produced per that 15 moles of methane. We can simply divide that, gives us 802.5 kilojoules per mole of methane. And this is your enthalpy change through combustion. Can also be written negative 802 kilojoules per mole. All right. Joseph Priestley prepared oxygen in 1774 by heating red mercury 2 oxide with sunlight focused through a lens. How much heat is required to decompose exactly 1 mole of red mercury oxide solids to mercury liquid and gaseous oxygen under standard conditions? I've drawn a little formula up here, and understanding this principle is important for solving this problem. We have tabulated values for the energy of formation, and that'll be written delta H sub F, I think. H prime sub F. Delta, of course, means change. This prime means under standard conditions, and the subscript F just communicates that this is the change in enthalpy of formation at standard state conditions. That value works forwards and backwards. So earlier we were talking about heat exchange of a solution being equal to the negative heat of the reaction. It kind of works the same way here. So if this value is, if the forward reaction is plus 50 kilojoules, the reaction going in the other way is going to be negative 50 kilojoules. Having that information, we can start to solve the problem. So let's go ahead and write down our reaction. We're going from solid red mercury 2 oxide. We want to decompose it into liquid mercury and gaseous oxygen. We refer to our tabulated values for mercury and oxygen. Make sure we're looking at the right one. Red mercury oxide and gaseous oxygen. So far, so good. Pull those values over. It's important that we also balance this equation, usually. And to do that, we would normally, because we have two oxygens on the right, we would want to throw a 2 over on the left and here. But because how much heat is required to decompose exactly 1 mole under these conditions? Um, that's why. Um, because the energy of formation for, or the change in enthalpy of formation for gaseous oxygen is 0, anything times 0 is 0, so we don't really need to worry about that. Actually, I'm going to leave those written up, but I'm going to cross them out since we don't need to worry about it. So we're going for the inverse because we're decomposing it. And our value was negative 90.83 plus 0 equals 90.83 kilojoules per mole. Actually, yeah, we don't need that part. Cool. Oh, we're making great time here. All right. So this is probably the most cumbersome problem we're going to deal with today. This is a Hess's law problem. Hess's law states that if a process can be written as the sum of stepwise processes, then the enthalpy change of the total process equals the sum of enthalpy changes of the various steps. So for the prompt here, the following sequence of reactions occurs in the commercial production of aqueous nitric acid. So the product of interest here is this aqueous nitric acid. To get there, we have these stepwise reactions and their associated enthalpy changes. Um, it is not enough to simply sum all of those values and hope for the best, because we have a lot of different molar quantities of each of these reactants involved in these processes, so we need to get them all equivalent first. The first thing that I like to do is highlight similar species and cancel out the ones that we can. So those that appear on both the right and the left, we don't have to worry about as much. So let's get this first one on the table. We've got 4NH3 plus 5 gaseous oxygen, 4 nitric oxide plus 6 H2O. I believe, well, I don't want to get ahead of myself here. Delta H equals negative 907 kilojoules. I'm rewriting this for a reason, I promise. In our next equation, we have 2 nitric oxide plus gaseous oxygen, nitrogen dioxide, negative 113 kilojoules. Now, to get this to line up, we have 4 nitric oxide on one side and 2 nitric oxide on the other. To fix this, we simply multiply everything by 2, and then we can sum those together. Make sure you can see that. Yep. Okay. So if we sum those together, we should then get negative 1,133 kilojoules. Okay. So that's our first one. Next up, we're going to go from yeah. So the NO2s can cancel out. We don't have to worry about them anymore. We've still got, we're going to carry these down, our NH3 plus we've got 5 plus 2, so 7 molecular oxygen. Two times 2 is 4 nitrogen dioxide, and 6 H2O. Now, hopefully this makes sense. I'm just carrying things down sort of below this line and making sure that all of our units stay the same, right? We're balancing both sides of the equations as we're doing this in a stepwise process. So now we're looking at the next step, and we've got 3 nitrogen dioxide plus water goes to sorry, 3 aqueous plus and before I forget, we need our enthalpy changes. We've got we calculated negative 1,133 kilojoules, and we are given negative 139 for this reaction. Okay, so now we need to get their least common multiple for each of these. And the one we can cancel out here is this nitrogen dioxide. 4 and 3, lowest common multiple would be 12, so that gets us 4 and 3. So we're going to multiply this entire thing by 3, and this entire thing by 4, gets us to 12. We end up with 12 NH3 plus 21 total oxygen. Excuse me. Yes. Yep. Some of the waters cancel out, not all. We get 14 H2O on the right side, none left on the left side. And 8 moles of our product. We can actually write that correctly. There we go. Plus 4 NO. So the last little bit we need to reconcile here, we also need to multiply these and add them up. and that's going to give us negative 3955 kilojoules. So that is the total energy change for the production of 8 moles of our product, right? I'm going to highlight this in green so it's clear that it's different. So for 8 moles of our aqueous nitric acid, we produce 3,955 kilojoules. And now we can simply run that equation to get the release per mole. And we should get a release of negative 494 kilojoules per mole of nitric acid. And that is our final answer. Okay, that's all I have for tonight. Again, live streams will be Fridays at 4 p.m. You will be able to find the recording of this live stream on the Portland State University YouTube Learning Center YouTube channel within an hour or so. Just needs time to process. If you have any questions, feel free to reach out, drop a comment. I will respond as soon as I am able. The tutors and learning assistants and career advisors and people at the Learning Center were all really supportive for me, and I like to pay that forward as much as I can. So happy to help in your academic pursuits, whatever that looks like for you. So I will see you all next week. Thanks for tuning in.